Hello everyone, welcome to this third video on application of Laplace for solving differential equation. The first two videos covered differential equations where the partial fractions were of individual, non-repeated or distinct factors, and the second case where you had the factor to be of the format a square plus 1. So we used as plus b method to solve the differential equation. In this part 3 video, we will be seeing the third technique of partial fraction method to solve for the differential equation. Come on, we will move into the video. We have been asked to solve dy by dt minus y equal to 1 minus 2t, and we have been given y of 0 is minus 1. Notice over here children that the derivative is just of dy by dt, which is first order. So since it is first order, just one boundary condition or initial condition is sufficient to solve the differential equation. So, if the order is 2, we require 2 conditions. If the order is 1, we just need 1 condition to solve it. So, we will be following the 4-step method to solve the differential equation. The first method or the first step is apply Laplace transform to the differential equation on both sides. The second one, apply the initial conditions or the boundary condition which has been given to you in the Laplace transform quantity. Third step, compute the partial fraction for the given expression. Step number 4, to remove the effect of the applied Laplace transform, at last we apply the inverse Laplace transform to the partial fraction. On applying all these 4 steps, we will be getting the solution of the differential equation, which is nothing but y of t. Okay, so now let us get started with this problem, which is of first derivative. We will have to recollect the formula for first derivative as we apply our condition number 1, which is applying Laplace on both sides. Apply Laplace transforms on both sides of your differential equation. So this gives me Laplace of, how I can replace this differential equation as dy by dt can be written as y dash of t minus, this is a simple y with no derivative, hence it is a function of t, is 1 minus 2t. When you apply Laplace to both sides, you have Laplace of y dash of t minus Laplace of y of t equal to Laplace of 1 minus Laplace of 2t. So this is our expression. What we require over here in the first term is Laplace of y dash of t. Recollect the formula for your first derivative of Laplace. So we know that Laplace of y dash of t is s times Laplace of y of t minus y of 0. So this quantity gets replaced as s times Laplace of y of t minus y of 0. Now, this term doesn't have a derivative, hence it is retained as such. So you have Laplace of y of t. Now coming to my right hand side, what do we know about Laplace of 1? Laplace of 1 is nothing but 1 by s. In the second term, this minus sign of 2 is a constant. What we have is Laplace of t. What do we know about Laplace of t? Laplace of t is nothing but 1 by s square. So you have this constant to be attached. So you have it as 2 by s square. Hence, the first step of applying Laplace on both sides is complete. What is the second step? Apply the initial conditions which has been given to us. We call it as initial condition since it is estimated at t equal to 0. So what does our initial condition say? Initial condition says y of 0 is minus 1. Where is our y of 0? This is my y of 0. So what I'll have to substitute for this y of 0? This y of 0 will be replaced by the quantity minus 1. So when I expand it, what will happen now? I will have this as s into Laplace of y of t, and the second term becomes minus of minus 1. So it is plus 1, and now this gives me minus Laplace of y of t is equal to let me take my LCM over here as s square. So s is missing. So this becomes s minus 2. Now try collecting Laplace of y of t so that the coefficient over here is s and over here it is minus 1. What is the extra factor? Is this plus 1. Take it to the opposite side. So you have this plus 1 to be replaced as minus 1. Now taking the LCM as s square, you have it as s minus 2 minus s square. So this is my right hand side. Now what we want is Laplace of y of t. So cross multiply this coefficient to the opposite side. Hence we have Laplace of your y of t to be equal to, the factor over here is going to be s minus 2 minus s square, s minus 2 minus s square divided by the denominator was s square, and when you push this s minus 1 over here, you will have s square into s minus 1. Now what is the third quantity we'll have to apply? Now I'll have to take the partial fraction. Partial fraction for the quantity s minus 2 minus s square divided by s square into s minus 1. Now this is going to be of our type 3 partial fraction. Type 1 being distinct factors in the denominator, type 2 being non-factorizable factor in the denominator, and type 3 repeated factor in the denominator. So now when you have a repeated factor, I will have to give individually, the total power is 3. So we need 3 constants. So we make it as a by s with a single power. Since it is a repeated power, I give one more constant b with the fraction s square. And for this independent quantity, I assume it to be c divided by s minus 1. So my partial fraction is set. So the next topic is to find values of a, b and c. Let us take the LCM. So it is s square into s minus 1. A has denominator as s. So what is left out is s and s minus 1. B has denominator s square. So the left out factor is s minus 1. C has s minus 1. So the left out factor is s square. Comparing the denominators on the first and the last term, they are the same. Hence the numerators have to be the same. So I have s minus 2 minus s square to be equal to as into s minus 1, b into s minus 1 plus c into s square. Now the objective is to find the values of a, b and c. Now how to get this value of a, b and c? Just substitute the values of the factors. So in the first case, let me put the factor which is s. So when I put my s to be equal to 0 on both sides, I have 0 minus 2 minus 0 to be equal to s equal to 0. So this will vanish. S equal to 0. So this will vanish. I will have b into 0 minus 1. So I have minus 2 to be equal to minus b. Hence b is equal to 2. I have got the value for my b. So for the second case, let me go for the second case and compare what is going to be the factor. The factor is s minus 1. If I put s minus 1 as 0, I will have s to be equal to 1. So I substitute s is equal to 1 on both sides of my equation. So when I substitute s as 1, I have 1 minus 2 minus 1 square is 1. And when I put s as 1 over here, 1 minus 1 becomes 0, 1 minus 1 becomes 0, and I have c times of 1. So this makes it as 1 and minus 1 cancels off. So c is given the value minus 2. I have estimated b, I have estimated c. So what will be the value of a now? How can I get the value of a? Only two factors are there. So let us go for the comparison. Let us compare the coefficient of s square on both sides. When I compare the coefficient of s square on the left hand side, the coefficient is minus 1. So this minus 1 is equal to s into s square's coefficient is a on my right hand side. B doesn't have a s square, so ignore it. How about coefficient of s square over here in the third term? It is going to be c. So I have minus 1 equal to a plus c. Already we know that c is equal to minus 2. Hence, when I substitute c to be equal to minus 2, the value of a is got as 1. So I have obtained the value of all the three constants a, b and c, a as 1, b as 2 and c as minus 2. Now what will be the next step? Go and fit it in your partial fraction in the positions of a, b and c. Now this is nothing but Laplace of y of t, which I had as s minus 2 minus s square divided by s square into s minus 1, which was a by s, b by s square and c by s minus 1. So now I have this as a's value is 1 by s, b's value is going to be 2 by s square, c's value is going to be minus 2, and then c's value is going to be minus 2, and this is going to be s minus 1. So I have Laplace of y of t to be this expression. Step number 4. From this Laplace of y of t, I need to retrieve back my y of t, which is the solution of the differential equation. So what will I do? I will go to apply inverse Laplace on both sides. When I apply inverse Laplace on both sides, this operators cancel off each other to give you y of t. Hence, I will be left out with Laplace inverse of 1 by s plus 2 times Laplace inverse of 1 by s square minus 2 times Laplace inverse of 1 by s minus 1. So now, having known the basic formulas for these quantities of Laplace inverse, I know that Laplace inverse of 1 by s takes the value 1 plus 2 times Laplace inverse of 1 by s square takes the value as t minus 2 times 1 by s minus 1 takes the Laplace inverse as e to the power of positive t. Hence, my final solution y of t is obtained as 1 plus 2t minus 2 e power t. Thank you.